Of course, we're more interested in other phase diagrams, not just a simple liquid-vapor phase. And so let's just take a look at one that's a little bit more involved. So here we have a liquid-solid phase diagram, and on the y-axis, instead of pressure, we have temperature. So on the x-axis, what we have is the mole fraction of sodium in a mixture of sodium and potassium. So this is a highly reactive mixture, so it's kept free of water and oxygen, etc. It's just pure sodium and potassium. And here is the phase diagram for it, showing all the phases that can occur at fairly high temperatures, actually 0 degrees Celsius. So actually you can get pretty low temperatures when you mix sodium and potassium pure with each other. But let's take a look at what we have here. We have a lot of different regions than we saw before. So I want to focus on this region here and we'll leave it up to the viewer to interpret what's happening in these other regions. Again, what we can do is analogous to what we did for the liquid vapor phase diagram we looked at before, where we can put an X in a region and look at the endpoints of that region and look at the length of the segments, and from that determine what we have in that region and determine how much of each phase we have in that region. So we can apply the same principle to this more complicated phase diagram. And so I can show you, put on a couple of annotations that will help us. Alright, what do we have? Again, I've put an X in the middle of this region, and I draw the endpoints and a segment connecting those endpoints. And the endpoints tell me what each phase is in that region, and the segment tells me how much of each phase I have. So this endpoint indicates that I have a liquid, because I'm next to the liquid phase, and that liquid is, if you look on the x-axis, about 45% sodium, which means that I have 55% potassium. The right endpoint is on a vertical line. And when you see a vertical line in a liquid-solid phase diagram, that generally means you have a specific compound. In this case, a specific compound consists of 2/3 sodium. So that must mean that since I have 2/3 sodium, I have sodium 2 potassium. So that's a specific solid compound. This line indicates I have a solid, and that solid has a stoichiometric ratio of 2 sodiums for every potassium. So that's what I have in this region indicated by this line, is sodium 2 potassium. So those are my two phases, one of which is liquid, and one of which is the sodium 2 potassium. Notice that the X is slightly closer to the liquid phase, and so that indicates that at the X, I have mostly liquid. If I were to shift this X to the right, and that would indicate that I have here mostly solid. So as I increase the mole fraction of sodium, it increases the amount present as solid. You could calculate this. You could take this line segment divided by the total length, and that would give you the fraction that is solid. And you could calculate the short segment divided by the total length, and that would give you the fraction that is present, or the fraction of the mixture that is liquid. Alright, again, the left segment indicates how much is solid, the right segment indicates how much is liquid. It's a little counterintuitive, but once you see where the X is, that it's closer to solid, it's easy to remember that little rule. And that's how to interpret tie lines.